In this last video, we're going to do two examples. This first example has two parts to one part. So please pause the video and write down the whole question. It'll help you understand what's going on with the problem, and you'll be able to annotate along with me. So please write down the whole problem. Note that here this is the mass of the baseball. I forgot to write it in early. So it's a 0.14 kilogram baseball, has a speed of 38 meters per second as it approaches a bat. The bat applies a force to the ball and leaves the bat with a speed of 58 meters per second in the other direction. The time of contact is 0.0016 seconds. And part A says calculate the impulse applied to the ball. So we need to know, well, hold on a second here. I'll write all three of the equations. I can write them here. I'll write down all the equations that we could possibly use to get impulse. So impulse is force times change in time. That's one of our equations for impulse, but I can't use that because we don't have the average force. What we just found in our derivation is that impulse is also the same as change in momentum. So if I can figure out the momentum of the baseball before and after the hit, I'll be all set. As a refresher, that's what momentum is, mass times velocity. Well, we've got the mass of the baseball, and we have the velocity of the baseball before and after. So here's what that'll look like. We're going to get those momentums, and we'll be able to figure out the change in momentum from that. So here we go. Here's what's going on before. Here's what's going on after. I'll draw a little picture for both. So it says the baseball, I'm going to assume it's moving right, is moving with a speed of 38 meters per second. Beforehand, it gets hit by the baseball bat and it goes in the other direction. So that's 58. What I want to do to get the change in momentum is I'm going to calculate each of these two momentums first. So before, that's the velocity, but the mass is always going to be 0.14. So here's how you calculate momentum. It's mass times velocity. 0.14 times 38. And dang, I didn't calculate it beforehand, but that's all right. 0.14 times 38. So we'll have 5.32. So that's our momentum before. Afterwards, we have a different momentum, but we got to be very careful with this one. It's going to be 0.14, and 58 is not our velocity. Our velocity is negative 58. Momentum is a vector, so we need to put in a negative sign if something's pointing. So since these are opposite directions, one of them has to be negative. I went with after. I said that it's going right and then it's going left. So 0.14 times 58, negative 58, will be negative 8.12, and our units are kilogram meters per second. I made a mistake over here. This is actually the wrong unit for momentum. It is kilogram meters per second. Okay. Keep in mind, we're trying to get impulse, and impulse is a change in momentum. Here's how we'll get our change. Change is always final minus initial. So the change in your bank account amount is your final bank account amount minus your initial bank account amount. That applies to momentum as well, and anything really, velocity, whatever. We've done that a lot. So change of momentum will be PF minus PO. That's final momentum minus initial momentum. So it'll be negative 8.12 minus 5.32. So we'll get negative 13.44 kilogram meters per second. That's our change in momentum. We could say that is our answer, or we can change the letter to be impulse. So there's our answer. Impulse and change of momentum are the same thing. Going on to part B. Part B is very simple. For part B it says calculate the average force applied to the ball. Well, there's only one equation today that has force in it, and that is the impulse definition. So we'll plug in everything we know. We're looking for force. She wrote down that part B. So I'm going to leave force in there. And delta T is the amount of time that the ball was in contact with the bat. If you look at what you wrote down, they gave us a time of 0.0016. Now that's a very small amount of time. It sounds crazy, but I mean, it happens in an instant. The crack of the bat, very short amount of time. So we'll divide both sides by 0.0016. And we'll have a lot of force, and that makes sense. That's exerted a lot of force. That's where the ball goes so far. And we'll get around negative 8,400, 8,000. So there's our first example. I'm going to take a look at the second one. I believe it's pretty short. Let's see what we can do with this one. So I kind of shortened the problem a little bit. Ignore this here. We're starting there. Rain is falling with a speed of 15 meters per second as it strikes the roof of a car. Ignoring gravity, calculate the force used by the roof to bring 0.06 kilograms of rain to rest in 1 second. Okay, so rain, so make sure you write down the problem, take a quick pause and write it down. So here's what we've got. I think this is kind of weird, but I'll just draw like a little roof of the car just to explain what's going on. And you can skip the drawing if you don't think it's necessary for you. So I don't even know how to draw a raindrop. I don't know, is that like a raindrop? Whatever. So a raindrop is hitting the roof of a car. It reaches the roof of a car with a speed of 15, and then the car is pushing up on it and slowing it down and bringing it to a rest. So it's going to like squish down, and then it'll just be like a little puddle, very mini puddle on there. So there's thousands of raindrops on here, but they're keeping it as like a summary. So they're just saying there's 0.06 kilograms of rain total. So maybe that's like 100 or 200 drops of rain at a time, and those are all hitting in 1 second. So basically, the only reason I wanted to show you this is to show you two things. The fact that V initial is negative 15. It's negative because it's going down. And then VF is 0. So this is one of those situations where we've been talking about it all year. A lot of people think that a velocity of a raindrop is 0 when it hits the tip of the car, the roof of the car, but really the final velocity is 0 a moment after. So gravity is pulling it down. Only when it reaches the roof of the car does the velocity become 0, and that happens because the car is pushing up. So it's not in free fall anymore when it hits a velocity of 0. While we're taking inventory here, why not just write down the rest of it? Mass is 0.06, and time is 1. And we're trying to calculate the amount of force. So let's see what we can do here. I haven't actually solved this one, but I'm gonna write down our equations. Let me see if I can fly through this with you. Don't write this down until I know that it's right. We're trying to get F, we have T, so we need J. Okay, so this is just like the last one where we're trying to get F, we have time, but in order to get impulse, we need to use the impulse momentum theorem. The fact that change in momentum and impulse are the same thing. So we'll get the change in momentum of the raindrop, we'll plug it in here, and then we'll continue. So let's go down below our picture to find this. So P initial is going to be mass times V initial. P final is going to be mass times V final. P final is easy because one of these is 0. Do you know which one? That's right, this one's 0. Final velocity is 0 for the raindrop because the roof of the car is stopping it. So that's pretty easy for us. P final is 0. P initial is pretty easy to find as well. It's 0.06 times -15. So make sure you're writing these down. We're like halfway done with the problem already. Maybe pause if you need to catch up. So P initial is -0.9 kilogram meters per second. I'm going to put a little box around that. And P final is 0. The whole reason of doing this part is to get our change in momentum, which is P final minus P initial. So 0 minus -0.9. So our change in momentum is 0.9. But what's our impulse? Well, our impulse is 0.9. Impulse and momentum are the same thing. So J is our impulse. It's also 0.9. So we are ready to solve the problem. Finally, over here, like we said, J is 0.9. F is the thing we're trying to calculate. And delta T is 1. So if we divide both sides by 1, we're just going to get the same value, 0.9. So there it is, example 2. Once you have it written down, send it to me on Remind. Thank you much.